Okay, let's just jump right in. For decades, there's been this one foundational idea about Mars that everyone agrees on.
Right. It's settled science, really.
That, 4 billion years ago, Mars was wet, it had rivers, lakes, maybe even oceans. The conditions were basically there, suitable for life.
Potentially habitable, absolutely.
Yeah.
But that's where the agreement sort of ends and the real mystery begins.
The big question.
The critical question, yeah. The thing every mission is trying to solve isn't if Mars had water, but for how long? How long did those good times actually last?
Because the standard models, the ones we've been working with for years, they paint a pretty grim picture, don't they?
Oh, very grim. The idea was that Mars's good days ended and ended fast. We're talking over 3 billion years ago.
Like a light switch being flipped off.
Exactly. The planet dries up, the atmosphere gets stripped away, and any life, if it ever got started, would have been wiped out or forced deep, deep underground.
But that's not what the data is saying anymore.
Not at all. And that's what's so exciting. The data coming back from NASA's Curiosity rover, specifically from its work in Gale Crater, suggests that whole timeline is just wrong.
It wasn't a sudden shutoff.
No. It opens the door to a much more complex and honestly a far more optimistic Martian past.
So that's our deep dive for today. We're going to unpack this new research, which focuses on these ancient sand dunes, now solid rock, that are hinting at water sticking around much, much later than anyone thought possible.
And we're going to explore what that means.
Right. We want to understand what these cemented dunes tell us about Mars's hidden groundwater history, and crucially, why they might be the single best place to look for ancient fossils.
It really does reshape the entire strategy for finding life out there.
Okay, so let's set the stage. Let's talk about that vanishing act, the accepted timeline. When did Mars lose its water and atmosphere?
Well, the environmental collapse is pretty consistently pegged to that transition between two big eras, the Noachian and the Hesperian.
And that is what, roughly 4.2 to 3.7 billion years ago?
That's the window. And the key trigger was the decay of Mars's global magnetic field.
Without that shield, it was completely exposed.
A sitting duck for the solar wind. It just steadily stripped the atmosphere away. And as that pressure dropped, the temperatures just plummeted.
With the water on the surface.
It had two choices. Either boil off violently into space or freeze solid.
So after about 3.7 billion years ago, the surface of Mars is basically the desert we know today. But this new research challenges that idea of it becoming instantly sterile. You mentioned these pockets of habitability.
Yes, because the surface became incredibly harsh, blasted with radiation, freezing cold. But life, or at least the liquid water it needs, it's really resourceful.
It finds a way.
It finds a way, and the evidence now suggests it just retreated, moving underground where it could stay liquid and shielded from the surface. Think of them like these little subterranean life rafts.
And Curiosity is finding the clearest signs of this in Gale Crater, right? At the base of Mount Sharp.
Correct. Gale Crater is a perfect geological laboratory for this. The layers of sediment there are like pages in a history book telling the story of Mars's water, and they've just found the smoking gun.
Okay, which brings us to the core evidence. The big surprise finding from the team at NYU Abu Dhabi. They were looking at these ancient sand dunes, and they saw something really unusual.
They did. They were looking at dunes in a place called the Stimson Formation, and they realized these dunes had been completely lithified.
Lithified, meaning turned to stone.
Exactly. Cemented, hardened into solid sedimentary rock. And this isn't just, sand that's been squashed together. This is a specific chemical process that takes a very long time.
And the mechanism behind that hardening is the key here. It implies a long, slow interaction with groundwater specifically.
Precisely. You see, if it was just surface water, a flood or something, you'd expect a shallow crust, maybe some quick erosion.
But that's not what they saw.
No, they saw this pervasive, deep hardening. That tells you that Mars had an active subsurface water system, a whole plumbing network that was active much, much later than any of our climate models predicted.
So we're talking about liquid water flowing underground maybe hundreds of millions of years after the oceans were gone.
That's what the evidence points to. It totally shifts the timeline.
When this work was published in the Journal of Geophysical Research, Planets, led by Dimitra Atre's team at NYUE.
That's right. And what's so amazing about the Stimson Formation is the paradox it presents.
How so?
Well, the sand itself, the dunes, they were deposited way back in the Noachian period, Mars's earliest, wettest era. But the process that turned that sand into stone, the hardening, That happened much, much later. The sand is old, but the cement is young, geologically speaking.
I see. So the stage was set in the wet era, but the final act needed this lingering source of underground moisture.
Okay, but I have to play devil's advocate. How can they be so sure? How do you look at a rock on another planet and say, that was groundwater and not, a flash flood or melting ice? That is a great question, and this is where the science gets really cool. It's like global detective work. They used Earth as their Rosetta Stone.
By using terrestrial analog.
Exactly. They basically pulled up the MSL Curiosity notebook, which is the rover's master log of every image, every chemical analysis, and they compared the Martian rocks to very similar formations right here on Earth.
So they're using modern geology to decode something that happened billions of years ago on Mars.
Specifically, they looked at the deserts in the United Arab Emirates.
The UAE.
Yes, because those deserts have these massive dunes that, despite being in an incredibly dry place, have also been cemented into rock. And the mechanism there is 100% known. It's groundwater.
Ah, so it percolates up.
Slowly, carrying dissolved minerals. And when that water gets near the surface and evaporates, the minerals drop out and act like a glue, binding the sand grains together.
That's an incredible parallel. But wait, Mars has way lower gravity, a different atmosphere. Isn't it a bit of a leap to assume the geology maps perfectly from a desert in the UAE?
It is a leap, but it's a very well-supported one. Because the structure of the rock, the chemical composition, is just so strikingly similar. Their conclusion was that the Stimson Formation had to have been formed by this late-stage aqueous activity.
Fed by groundwater flowing from Mount Sharp.
Most likely, yeah. Moving slowly down the pressure gradient from the mountain. And it wasn't just plain water, it was carrying the evidence with it.
Mineral clues.
Exactly. The big one they highlight is gypsum.
Which is a calcium sulfate.
Right. And gypsum forms in Earth's deserts through this exact same slow groundwater evaporation process. Finding gypsum cemented inside those Martian dunes it seals the case. This is mineralogical proof.
And this wasn't just a one-off finding, right? It builds on other work in Gale Trader.
Oh, absolutely. It's part of a bigger picture that's emerging. Earlier work from the same team looked at the Green Hue Pediment, which is another ancient dune system nearby.
And they saw the same thing.
The exact same pattern. Ancient dunes, hardened by later interaction with subsurface water, trapping minerals like gypsum. When you see it happening in two different large-scale regions, you know it's a real crater-wide phenomenon.
Okay, so we've got these hardened dunes, and we've got how this persistent late-stage groundwater. So now let's make that leap to the so what, the big one. What does this mean for the search for life?
It means we may have just found our #1 top priority target for finding microbial fossils.
Why this specific type of rock? Why is this sandstone so special?
Because here on Earth, sandstones formed by this very process are where we find some of the oldest traces of life ever discovered.
Is it something about the minerals or something the microbes themselves are doing?
It's both, but it's mainly what the microbes do. It's a process called biomineralization. See, microbial communities, bacteria, fungi, they can actually bind sediment grains together. As they live in the porous sand, their metabolism changes the local chemistry. They often secrete these sticky substances that trap the grains, and that process actually encourages minerals like gypsum to precipitate out of the water.
So the microbes are basically building their own fossils. They're acting like tiny little engineers, laying the concrete for their own preservation.
That's a perfect way to think about it. They leave behind these permanent, detectable signatures. When the minerals form around them, they trap the microorganisms, leaving behind either their physical shape or, molecular fingerprints sealed inside the rock.
That is it's a thrilling, almost haunting idea that the very process that turned the sand to rock could have also been preserving any life that was there, sealing it in for billions of years.
That is the core hypothesis of this research. Given the parallels to Earth, the researchers flat out proposed that these lithified dunes may contain preserved remnants of ancient Martian microorganisms. We've moved beyond just looking for water. Now we're looking for the geological record that life leaves behind.
This really does change the entire narrative. The story of Mars isn't this sudden catastrophic shift from a wet world to a frozen desert.
Oh, it's a much more gradual, drawn-out process. And that means these environmental niches, these groundwater systems, they could have persisted for far longer than we ever thought.
Which gives life, if it ever got a foothold, A much longer window to adapt.
A longer time to survive, to evolve, to retreat into these protected underground environments. It just fundamentally expands the window for Martian habitability.
And on a practical level, this gives future missions, like sample return missions, an exact target. We don't have to just drill randomly anymore.
Right. It tells us exactly where to go. These groundwater-altered dunes are prime real estate for finding biosignatures. We can guide future rovers right to the spot where fossil evidence is most likely to be waiting.
We're moving from a general search to a focused hunt.
A focused hunt for biosignatures, exactly. The priority is now drilling deep into these late cemented rocks and bringing those samples home. It's a huge shift in strategy, all because of these tiny details in an ancient Martian dune.
It's just amazing. It really proves that Mars's history is so much more nuanced than we gave it credit for. The big takeaway here is that habitability didn't just turn off like a light switch.
The door was kept open.
For much, much longer. And these subsurface water systems turned ancient sand into what are essentially biological time capsules. It's not just about the water anymore, it's about time.
And that leads to the final provocative thought we want to leave you with. Building on that idea of life preserving itself in stone.
Okay.
If microbes on Earth leave these distinct physical and chemical signatures by binding sediment together, what specific, almost imperceptible geological signatures should we be looking for in that Martian gypsum? What patterns in the rock could only be explained by life?
So not just looking for organic molecules, but for a structure.
Exactly. The microscopic equivalent of a footprint in cement. Something that proves biology, and not just chemistry, was at work. The answer to the question, was there life on Mars, might not be in the composition of the rocks, but in their actual texture.
For the complete news, visit our website. Support us by following and sharing.